I'm Dr. Courtney. A couple of years ago, two colleagues and I wrote a paper called 5 Frequently Fatal Freshman Physics Fantasies. Now, the first of these we termed the fantasy of the miracle finish. This is a favorite film of mine. It's called Miracle, and it tells the story of the 1980 U.S. Olympic hockey team which defeated the Soviet team in the gold medal round. That was considered a miracle by many because the Soviet team was disciplined, they were professionals, and they were used to winning. Now, what you learn as you watch the film is that the miracle didn't actually happen that day of the contest. It had happened over many occasions previous on the practice ice. Now, you may feel you need a miracle to succeed in physics, and I believe that miracle can be yours, but you'll need to practice. In this problem, we are asked to compute the acceleration of the moon as it orbits the Earth when we are given the radius of that orbit and the period, or the time it takes to complete one orbit. If we assume that the angular velocity of the moon is constant, then we can apply the principles of uniform circular motion to do this. We will use the symbol A for acceleration, and we've been given the radius, which we'll call R, and the period, which we'll call T. As we develop this problem, we'll draw a sketch to represent what's happening physically. Then we'll make a point-by-point plan to follow when we evaluate the problem. We are told that the orbit is nearly circular, so our mathematics can assume a circular orbit. We are given that the radius of that orbit is 385,000 kilometers, and that the period is 27 days. As we begin to evaluate, we're going to want to look at the units first of all. We want to check and, if necessary, convert our given values to MKS units. Then we can recall the relationship used to describe uniform circular motion, which is that the acceleration is equal to the square of the velocity over the radius. Now, if we take a moment to consider what we've been given and what terms are included in this expression for uniform circular motion, we see that velocity is required, but we were not given velocity. So we need to think for a moment, can we compute velocity or express velocity in terms of values that we have been given? And yes, we can. So that will be the next step in our plan, will be to express the velocity in terms of the radius and the period. Then we can substitute for the velocity that new expression into the expression for uniform circular motion. Since A is already isolated, the acceleration, and that's what we're looking for, we would then be ready to substitute specific values for the radius and the period to compute the acceleration. And before we report our final answer, we want to consider how many significant figures to use. Let's take a look at our units. Well, units of kilometers and days are not MKS units, so both of those values will have to be converted. If we have 385,000 kilometers times 1,000 meters per kilometer, this yields a large number, so I'm going to use scientific notation to make it more compact. 385 times 10 to the 6th meters. Similarly, 27 days converts to, we have 24 hours in a day and 3,600 seconds in an hour. This also yields a large number that we will express as 2.3328 times 10 to the 6th seconds. Next, we will recall the relationship for uniform circular motion, that the acceleration equals the square of the velocity over the radius. And we need to express that velocity in terms of values that we've been given. Now, velocity is defined as the distance traveled over a time. The distance in this case is the orbit. If we assume the orbit is circular, we can represent it as the circumference of that circle, or 2 pi times the radius. And then divided by the period, or the time it takes to travel that distance, will give us the velocity. Then we'll substitute for velocity in the equation for uniform circular motion. So we'll have 2 pi r over t, quantity squared, all over r. Let's simplify that. 4 pi squared r squared over t squared, all over r. This r in the denominator cancels with one term of r in the numerator. So we can express that a little bit more simply as 4 pi squared r over t squared. Now we're ready to substitute values for the period and the radius. So we have 4 times 3.14 squared times 385 times 10 to the 6th meters for the radius, and divided by 2.3328 times 10 to the 6th seconds squared for the period squared. This gives us a value of 0.00279 meters per second squared. Let's consider our given values. We see that the smallest number of significant digits is 2, so we should also round our answer to 2 sig figs. So the acceleration is 0.0028 meters per second squared. We have a value now for acceleration, but how do we know whether it's reasonable? As we assess our answer, we can take several approaches. The first is to consider units, not whether we're in MKS units, but whether the units that we come out with in our calculations match the type of thing we're trying to compute. So as we substituted for the radius and for the period, we included units of meters and of seconds for the period. So we come out with meters per second squared for acceleration, and that is the unit that we would expect. Next, we want to think about the magnitude. That's a small number. We were dealing with some very large numbers. How do we know whether our answer is in the right ballpark? Well, let's think about physically what's happening. The acceleration due to gravity on the surface of the Earth is about 9.8 meters per second squared, and the Moon is much further away from the center of the Earth than the surface of the Earth is. So we would expect the acceleration being experienced by the Moon to be much less than the acceleration on Earth's surface. So we can write that briefly as we expect A to be much less than the acceleration due to gravity, 9.8 meters per second squared, and indeed it is much less, because that acceleration falls off as the square of distance from the center of the Earth. Third, if you're still not confident in your answer, I would suggest repeating your calculation. It's not particularly difficult, but it is tricky for a couple of reasons. When you're dealing with scientific notation and powers, it's easy to make a mistake on order of operations on a calculator. Also, it's easy after you've already expressed something in scientific notation to remember to square it. The first time I did this problem, I forgot to square the time and came out with an answer 6 orders of magnitude larger than this one, which, given our second way of assessing our answer, doesn't make sense at all. So in a problem like this, it's worth it to take a few extra seconds and repeat your calculation. Between the unit analysis, the physical considerations, and double-checking our calculations, we have confidence that this answer is correct.